Have you ever just stared at a jumbo jet and thought, how in the world does that thing get off the ground? I mean, we know the engines are pushing it forward, but what's actually pushing it up? Well, you might be surprised to learn that the secret to all of it, from a gentle takeoff all the way to supersonic flight, it all starts with the physics of perfectly still air. Let's get into it.
So that's the big question, right? What is this invisible force that just completely defies gravity on such a massive scale? The answer, believe it or not, is all around us, in the very air we're breathing. And it all begins with a concept called static pressure.
All right, here's our game plan. We're going to start with why stillness is so critical. Then we'll actually define the force we're talking about, pressure. After that, we'll see how it changes, apply that to the real world, our atmosphere. And finally, check out how planes literally read the air to fly.
Okay, first up, why on earth does stillness matter? I know, it sounds a little backwards. To understand how a plane flies at hundreds of miles per hour, we have to start by looking at fluids that aren't moving at all.
And there's a whole field for this. It's called fluid statics. It's the pure physics of fluids, and remember, air is a fluid just like water. When they're totally at rest, velocity is zero. Now, this isn't just some abstract theory. It is the absolute bedrock that every single aerodynamic calculation is built on. So why do we care so much about still air? Because the entire magic of lift, that force holding the plane up, is created by a careful distribution of pressure all around the wing. And to get how that works, you first have to nail down the rules of pressure when nothing's moving. If you skip this step, lift just feels like, well, magic.
All right, let's get to the star of the show, pressure. This is that invisible force that, when you learn how to control it, makes flight possible in the first place.
At its very core, pressure is actually beautiful and simple. It's all right here in this one little equation. Just 3 letters, but trust me, those letters hold the key to everything from generating lift to measuring how fast you're going. So what's it all mean? Well, pressure, or P, is just the amount of force, F, that you're applying over a certain area, A. You know, think about the difference between pushing on a wall with the palm of your hand versus pushing it with just the tip of your finger. You're using the same force, but the area is way different, which means the pressure is completely different. Now here's where it gets really interesting. In a fluid, pressure behaves in some specific ways. It's not just a push in one direction. It pushes equally, in all directions, all at once. It always acts at a perfect right angle, perpendicular to any surface it touches. And if you're at the same depth or altitude in that fluid, the pressure is exactly the same no matter where you are. These rules are going to be super important in a minute.
Okay, so we know what pressure is, but here's the thing. It's not constant, it changes. So let's look at the fundamental law that tells us exactly how it changes when you move up or down through a fluid.
I know, this equation might look a little intense at first, but don't worry. This is called the hydrostatic equation, and it's basically the master key that unlocks how pressure changes with altitude. For an engineer, this is the tool to precisely calculate the force of the air at any height.
Let's just tear this thing apart real quick. On the left, dP over dz, that's just a fancy way of asking, how much does pressure change when my height changes? And the equation tells us that change is equal to the fluid's density, that's the Greek letter rho, multiplied by gravity, g. But look, that little minus sign, that's the most important part. It tells us, without a doubt, that as you go up, pressure always goes down.
So the crucial insight here, the big takeaway is this. The pressure you feel in any fluid, whether you're deep in the ocean or high in the atmosphere, it all boils down to just 3 things: how dense that fluid is, the pull of gravity, and how high or deep you are. So let's take that law out of the textbook and apply it to the biggest fluid we all live in, this massive ocean of air that we call the atmosphere. And this just shows you the effect perfectly. Down here at sea level, you've got over 100,000 pascals of pressure pushing on you from the weight of all the air above. But climb to 10 kilometers, about 33,000 feet, where jets cruise, and look at that. The pressure plummets to just a quarter of what it was.
And for an aircraft, this has massive consequences. High altitude means low pressure, and low pressure means the air is way less dense. It's thinner. So to get enough lift out of that thin air, the plane has to do one of 2 things: either fly a lot faster or have much larger wings to grab onto enough air molecules.
So if pressure is so incredibly important, how does a pilot actually know what it is? Well, let's get into our final section and see how airplanes have been engineered to literally read the air and use these principles to fly. To understand this, we need to meet a new character, dynamic pressure. Think of it like this.
Static pressure is the baseline pressure of the air just sitting there. It's what relates to your altitude. Dynamic pressure, on the other hand, is the extra pressure you feel because the air is moving. It's the force of the wind hitting your face when you stick your head out of a car window. And that is what tells you your speed.
And what's really cool is how they relate. It's incredibly simple. The total pressure that a plane feels is just the static pressure of the atmosphere around it, plus the dynamic pressure created by flying through the air. And that's it.
So here's how an airplane cleverly uses that simple equation to figure out how fast it's going. There's an instrument called a pitot tube that faces straight into the wind, and it measures the total pressure. Then there are little holes on the side of the plane called static ports that measure just the static pressure. The plane's computers just subtract one from the other. The result is the dynamic pressure, and from that number, it can calculate its airspeed with incredible precision. Just a brilliant piece of engineering.
Now, if you really want to get into the weeds, engineers use a more precise version of this called the barometric formula. It builds on what we've learned but adds in other factors, like changing air temperature. But the key thing to notice here is that new letter, E. That represents an exponential function.
So what does that E really mean for us? This is maybe the most critical insight of the whole thing. It means the pressure drop as you go up isn't a nice, straight, steady line. It's a curve, an exponential curve. The higher you go, the faster and faster the pressure disappears. Understanding this curve is absolutely essential for designing aircraft that can fly safely and efficiently right at the edge of our atmosphere.
Okay, let's do a quick recap. We started with fluid statics, the physics of still air. We defined pressure as force over area and saw how it always decreases with height. We then learned how that pressure drop affects how a plane has to fly. And finally, we saw how aircraft brilliantly use the difference between total and static pressure to figure out exactly how fast they're moving.
We've seen how pressure works, and we've seen how we measure it. But that really leaves us with one last huge question. If this invisible force is the key to both lift and speed, then how exactly do engineers shape something like an airplane wing to manipulate that pressure with absolute perfection? Well, that's a story for another time.